Chapter 9: Statics and Torque Implemented in Machines and Muscles. Have you ever wondered why a seesaw balances perfectly, or how a wrench makes loosening bolts so much easier? These everyday moments are examples of static and torque at work. Statics is the study of forces that keep things stable, like bridges and buildings. Statics is about balance. It tells us that for something to stay still, the forces pushing or pulling on it must add up to zero. We write this as. This equation comes from the idea of equilibrium, which means something isn't moving. For an object to stay still or move at a constant speed, not speeding up or slowing down, all the forces acting on it must cancel each other out. Torque, on the other hand, explains how forces cause rotation, like swinging a door or spinning a Ferris wheel. Torque explains how things turn. It depends on three things: the force you use, how far from the pivot you push, and the angle you push at. Here, r is the distance from the pivot point, the center of rotation, to where the force is applied. The farther away, the easier it is to turn something. F is the force you apply. More force means more turning power, and sine delta is the angle of the force. If you push straight at the pivot point, there is no turning effect. If you push at a 90-degree angle, you get the maximum torque. Together, statics and torque form the foundation of countless designs and tools in our world. Simple machines are tools that make work easier by reducing the effort needed to move an object. While they don't change the amount of work done, they allow us to apply smaller forces over greater distances. One important concept in simple machines is mechanical advantage. This tells us how much a machine multiplies our input force. We calculate it as output force divided by input force.
Now let's apply what we know from simple machines into this wheelbarrow in this free body diagram, shown in the illustration above. Now we know that the given values are the mass of the wheelbarrow, of course being 45 kilograms, the distance from the pivot point to the input force, being 1.02 meters, and the distance from the pivot point to the output force, just being a mere 0.075 meters. Now, given all these values, we're going to calculate the force exerted to support the wheelbarrow and its load. Now remembering from the last slide, we were to remember mechanical advantage equals to the output force divided by the input force, which also equals to the distance from pivot point to the input force divided by the distance from pivot point to the output force. Now, before moving around the equation, one equation that we do got to remember from the second law of motion from Newton himself, force equals to mass times acceleration, because as we are shown here in this wheelbarrow, we are not given a value for the output force, but we are given one thing, the mass. But I will further explain later on how we will get the acceleration for it, so we can get the force of output, the output force. Now moving around the equation, as shown to the right of the free body diagram, we will be ended up with the input force will equal to the output force multiplied by the distance from pivot point to the output force, all that divided by the distance from pivot point to the input force. Now, remembering from what I said earlier, force equals mass times acceleration. Now, we don't really have an acceleration from the x-axis, but we do have an acceleration from the y-axis, gravity. The acceleration for gravity will be 9.8 meters per second squared. It's universal. One has to remember that. Now, plugging in the numbers into the equation. As one can see, for the output force, 45 kilograms times 9.8 meters per second squared will give us the output force. Now multiply the output force by the distance from pivot point to the output force, being a mere 0.075 meters, all that divided by the 1.02 meters, which is the distance from pivot point to input force. It will finalize and give us 32.4 newtons. What does this mean? It means when one picks up the wheelbarrow, you exerted 32.4 newton force, so you can support the whole wheelbarrow. Now, we have another example as shown in the next slide. Now, Within this example, we are given the same wheelbarrow as last slide. Same values, same everything. Some of the values from the last slide will also be transferred from the last slide into this slide. Keep that in mind. Now, within this example, now we'll calculate the force it exerts on the ground. Now, looking at the free body diagram, we are given N, which means the normal force, the input force, and the weight, which is the weight is the only one pointing down. Using the free body diagram, we know that the normal force plus the input force, well, it's the other way around here in the equation, but y'all get me, equals to the weight. Now, moving this equation around, since we just want to know the normal force of the whole equation, we'll subtract the input force from both sides, and we'll be left with the normal force equals to weight minus the input force. Now, also remembering from the last slide, weight, we calculated it by using the second law of motion from Isaac Newton. That being, force equals to mass times acceleration, force being the weight, equaling to the mass, which is given as 45 kilograms, but the acceleration, since the weight is working on the y-axis and it's pointing down, the acceleration is given to us by gravity, being 9.8 meters per second squared, minus the input force, which, given from the last calculation from the last slide, was 32.7 newtons. Now, here is the weight, as I explained to you how we got it. And inputting the numbers so we can calculate normal force, we get 409 newtons. Now guys, remember to always follow significant figures, as shown within these two examples.
That's an example of how the physics behind a wheelbarrow machine works, but it is highly improbable that the average person will use a wheelbarrow in their daily lives. So, let's delve into another use of forces, statics, and torque that we might see more often now that the holidays are coming around. Let's take a look at how a bicep muscle and its joints work in terms of its forces, statics, and torque in order to hold a cookie tin up for guests to grab from. It is important to note that for this scenario, we will be assuming that the mass of the cookies inside the cookie tin does not change, presumably before any guests grab a cookie. A forearm holding up an object, such as in the illustration, demonstrates forces very similar to that of a lever system. The bicep muscle, indicated by the portion in red, acts as a flexor, meaning it closes the limb, and the tricep muscle, indicated by the portion in orange, acts as an extensor, meaning it opens the limb. This is important to note when determining the direction of the torques due to each force. Since most muscles exert larger forces inside of the body compared to externally, their mechanical advantages are significantly smaller than one. Therefore, their input force is greater than their output force. First, like with any system dealing with forces, you want to start by drawing a free body diagram. In this scenario, there are 4 forces acting on the forearm and the cookie tin. FB represents the magnitude of the force of the biceps. FE represents the magnitude of the force of the elbow joint. WA represents the weight of the forearm, and WB represents the weight of the cookie tin. These will be further explained once all the values of the example problem are established.
After hearing how statics and torque can be related to our muscles in our body, why don't we try to apply what we learned by going over an example problem? Let's say that one of the guests who took a cookie from the cookie tin you're holding asks you to calculate the force exerted from your bicep muscle. So, to start this problem, it is important to identify any known values, including any forces acting on the forearm. Here we see a picture of the forearm holding the cookie tin. With this, you can identify a total of 4 forces acting on the forearm: WA, WB, FE, and FB, which is actually the force that we want to calculate in this problem. However, before making our calculations, it is important to know which equations will be used. For this problem specifically, we will be using the equation torque equals R times F times sine theta. In addition, it should be noted that the net torque in this problem should be equal to 0, since this system is in equilibrium. Additionally, for any problem in physics, it is important to draw a free body diagram. Like I mentioned, since there is 4 forces acting on the forearm, 4 arrows should be drawn in our free body diagram, where FB is directed upwards, and FE, WA, and WB are all directed downwards. This is because FE, WA, and WB are all forces that would produce a torque in the clockwise direction, relative to the pivot point in this problem, which would be located at the elbow, whereas FB would be the only force to produce a torque going in the counterclockwise direction. So with both our free body diagram and the picture of the forearm as reference, let's finally begin with our calculations. Let's start with a summation of torques. Here we see that when adding up all the torques, it should all equal to 0, due to being in equilibrium, though it is important to note that only 3 of the 4 forces are being added. This is because one of our forces, FE, would produce 0 torque since the distance relative to the pivot point would be 0. Another thing to take note of is that both the forces of WA and WB are negative since they are in the opposite direction to FB. Once we understand that only 3 forces are being added, let's try to identify some of the variables in our equation, starting with WA and WB, or the weights. To find the weight, we will be using the equation where weight equals mass times the acceleration due to gravity. As a result, the weight of the forearm is calculated to be 39.2 newtons, or 39 newtons when considering significant figures. And the weight of the cookie tin is calculated to be 49 newtons. Another variable we will need is R. Even though R is already given to us in the picture, we must first convert these values from centimeters to meters, using the conversion factor 1 meter equaling to 100 centimeters. So after using the conversion factor, we see that 18 centimeters becomes 0.18 meters, 44 centimeters becoming 0.44 meters, and 5 centimeters becoming 0.05 meters. Lastly, for theta, since the picture depicts the arm being at a right angle more or less, our theta in this problem will be 90 degrees. So now that we have all our variables, we can then plug these values into our equation to look like this. After calculations have been made using our inputted values, we see that the torque of the forearm is negative 7.02 Newton meters, and the torque of the cookie tin is negative 21.56 Newton meters. We also have the torque of the bicep muscle, which ends up to be 0.05 times FB, where we still don't know what FB equals to. In order to do this, we can add the torques of the forearm and the cookie tin on both sides, resulting in our new equation 28.58 Newton meters equals to 0.05 FB. We can then divide 0.05 from both sides to isolate FB. As a result, the force of the bicep muscle should be calculated to be 571.6 newtons, or 570 newtons, since the values inputted in our equation all had 2 significant figures.
Statics and torque are more than just physics concepts. They are the forces shaping the world around us. Statics ensures stability, keeping bridges standing and buildings secure, while torque drives motion, from turning a steering wheel in a car or pedaling a bike.